Hello, welcome to this lecture on Introduction to Machine Learning. I recorded this lecture as an introduction to a machine learning course for engineers. However, the lecture is fairly general in its sense, hardly has any mathematical concepts or engineering concepts. Most of it is just common sense, so it should be accessible to a wide variety of audience, and this can probably be helpful for people like managers who are going to be working with machine learning engineers to basically ask some critical questions that sometimes an engineer very focused on machine learning models and its accuracy and its performance may not have thought about. So the questions that will be answered in this talk are: is machine learning a fad? What is machine learning and how is it related to AI, neural networks, and deep learning? What makes a problem good or bad for machine learning? How should one critique a machine learning model? And what questions should be asked beyond the performance of a machine learning model? And then we'll also look at some myths and realities related to machine learning. But by the time we get to it, hopefully you should be able to answer those questions yourself. All right, let's get into it. All right, so is machine learning or AI ML, is it just a fad? So there have been many fads in the last 30 years and of course over the last several centuries. But you have to look at these fads not just as fads, but because some of them have actually delivered also. So if you think about the last 30 years, there was a time when programming, data structures, databases, IT, those were like big buzzwords. All colleges, VCs, and grant agencies were chasing those. And after that, it was computer networks, wireless communication, Web 2.0, etc. And then there was also a big buzz about nanotechnology. Now, some of these have deeply affected our economies and society and have reached a level of maturity from the point of view of ongoing innovation. So we take them for granted. They have become seamlessly integrated with the products and services that we use in our daily lives. So, for example, wireless communication and computer networks would be one of those, right? And programming and data structures would also be another one. Now, compare that to something like nanotechnology, which had a lot of promise, and it has delivered on certain fronts, but not to the extent that to the extent that there was excitement about nanotechnology. Perhaps because we discovered that there were challenges that we did not foresee until we started working with that technology. And once we overcome those challenges, perhaps the the excitement about nanotechnology would increase even further. So if you think about technology as the life cycle of technology, you might have seen this diagram uh, in many places. So you have time on the x-axis and the value of the technology or the investment in the technology on the y-axis. And what you see is that initially it starts with a low value, and then suddenly there's a lot of innovation going on, and because there's investment and value being created, it reaches a certain level of maturity, and after that you see a decline. Now, I want to challenge this notion little bit, that it's not always decline. It might be decline from the point of view of investment in innovation. So sometimes it's just commodification. So it has reached a level where there's not much innovation going on, but it has seamlessly integrated into many products and services that it has made a big impact on our lives, and because of that we don't think about it twice anymore. The other notion that I want to challenge here is that sometimes this curve is not just a curve with a single hump, right? So we discover some challenges in technology, then some other technologies develop that help this technology, or some innovators, uh, they overcome certain barriers to making the technology more useful, cheaper, smaller, etc. And because of that, there's a new wave of innovation. So you might be riding on a second curve. That's kind of what has happened to machine learning, with especially with the advent of deep learning. So we'll come to that in a bit. So machine learning is now being deeply embedded into our economy and society, and some of these examples you would realize immediately when you look at it. So, for example, if you post something on social media, faces are being automatically recognized and tagged, right? And then objects are being recognized. You might have seen news about companies that can automatically detect diseases in computed tomography, in CT scans. And if you pick any phone now, there is voice assist. So conversion of voice to text. It's all based on machine learning, right? You cannot be programming each and every person's voice, their tone, their accent, and and hope that the computer will extract the words out of it. It's all based on machine learning. And then for chatbots to work, for queries to work, and for translation from one language to another to work, all these things that we now seamlessly take for granted on some of these from some of these large technology companies, they're all driven by machine learning. And then time series prediction, such as prediction of stocks, a lot of trading has gone algorithmic. And uh, also things such as planning power generation based on predicting power consumption. Some of the things that are going to come in the near future that are not there yet are related to automatic decision making. That's the next frontier in machine learning, and powered by machine learning. There are other subsets or sub disciplines within machine learning that are working towards that. So these would be economic decisions such as customer targeting, credit approval. Some of this is already uh, being some of this is already using machine learning, but simpler models for now. And then other more complicated tasks such as autonomous driving. There's a lot of buzz about autonomous driverless cars that have been being developed by several companies. Then we'll also have things such as autonomous drones and robots. You must have seen uh, videos of robots with legs that can walk very well, and even if you kick them, they come back to their legs again, and they can walk again. So a lot of that is based on machine learning. And then critical decisions such as medical diagnosis, criminal forensics, and so forth. A lot of that we will see that it will go towards machine learning. So what exactly is machine learning? How does the training and the prediction work? So basically you can think of two phases in machine learning. The first phase is the training process, and the second phase is the prediction or the deployment process, deployment phase. So in the first phase, what you have is you take a lot of input data and you combine it with labels. So this is all supervised machine learning. Most of the advances are in what is called supervised machine learning. Um, so you take a lot of labels. So for example, you will take images and you will label it as a cat or a dog or a car or a person, etc. And with this paired information between inputs and their labels, we will learn a model, right? So this model is basically a big mathematical model that can take the input and compute the label, right? So once the model is performing to a certain level of accuracy, what we can do is we can deploy it, and then it will make prediction on future data where we won't need the labels, and that's the whole point. We want the model to give us the label. So we will give the input to the model that was obtained during the training phase, and it will give you the labels. So now let's look at how these terms are related: artificial intelligence, machine learning, neural networks, and deep learning. So artificial intelligence is sort of like an umbrella term. So whenever a machine has a behavior that is non-trivial, we call it artificial intelligence. But it doesn't have to be based on learning. It could be based on a fixed algorithm that you code a series of steps, and those steps are very complicated, so it seems as if the machine has some intelligence. However, machine learning is a subset of techniques under artificial intelligence where the behavior depends on the data used for training. So I may have one particular machine learning algorithm, but it will give me two different models if I use two different data sets to train it. I can use the same model, I can use the same algorithm to train a model to recognize different species of flowers and different species of birds, right? And that model A for flowers will not work for data B, which is birds, and the model B for birds will not work on data for flowers very well. So it all depends on what data was used for training. So it's in that way these algorithms are not fixed. They can change based on the data that was fed to them. Now, within machine learning, there's a class of algorithms which are called neural networks, and these or framework rather. Let me put it that way. It's a set of frameworks that are called neural networks. It's basically a structure of these machine learning models. It's a layered structure which was inspired initially by the human brain. We have layers of neurons. The idea being that each unit or each neuron does a very simple job. It has a very simple function, but because they are arranged in a network, they become a more complex machine, and that's what makes it scalable. Other machine learning models, other than neural networks, there are very few other types of frameworks that are scalable because they're based on these simple interconnected parts. So that is the critical thing why there's the second revolution in machine learning is because of these neural networks. Within these neural networks, there are certain types of neural networks where we can add several layers because of how they are interconnected. So because the interconnection has a certain structure, it is amenable to training very deep networks. Otherwise, these deep networks, before these structures were discovered, could not be trained very well. So these are deep and large neural networks. So why machine learning now? Why is this second wave of machine learning making such big headlines and and is wowing the world? So there are a couple of things that have come together, a couple of phenomena that have come together, a couple of developments, right? So first of all, we have lots of data now. We have inexpensive storage, we have inexpensive collection and transmission of data. So because of that, we are collecting a lot of data, whether it is images, whether it is videos, whether it is audio, whether it is text, whether it is customer transaction data, etc. So a lot of that is being collected, it is being digitized and so forth. And then the compute has become very cheaper. So we have server farms that you can rent for specific purposes for very affordable prices. And then this whole idea of using graphics processing units, these GPUs were coprocessor that would be put in gaming PCs or in graphics PCs to render things on the screen. Turns out the mathematics that these uh, processors are good at, the GPUs are good at, can be it is very similar to what is needed for deep neural networks. So these GPUs were repurposed by some engineers to basically train these neural networks in a massively parallel way. So for example, if your CPU has anywhere from 4 to 16 cores, these GPUs will have hundreds to thousands of cores. Each core is not as powerful as a CPU core, but because there are so many of them, it gives basically gives you a parallel, massively parallel computer within a desktop. And then of course now there are GPU farms where you can uh, search for the right structure of the neural network by shooting a training job onto many servers together, right? So now there are new frameworks and algorithms, especially in the deep learning area, that can make use of this lots of data, this large amount of data, and the computing power. So you might have heard of names such as ResNet and GPT, GPT-3, etc. So these are like these very large neural networks based on deep learning structures, which means that they have special way of connecting these neurons that makes them amenable to learning even if they have many neurons. So these have done wonders on structured data such as images and text. But machine learning is not a silver bullet, right? It will not solve all your analytical needs, all your prediction needs, right? So in what cases will it not be a good framework for the kind of analytical needs that you have? So if you're not sure of what the desired output looks like, right? So if you don't know what is it that you want to predict, let's say you just want to you just have a lot of unstructured data and you want to see what are the trends in that. You're better off doing something like data science and data discovery than actually jumping into machine learning. A lot of unsupervised learning, machine learning has not, I mean, there have been advances in unsupervised machine learning, but not to the same extent as supervised machine learning. For supervised machine learning, you have to have the labels, which means you have to have the desired output in mind, and you have to have that desired output written for thousands and millions of examples on which a machine learning model will be trained. So if you have too little data, then machine learning does not easily generalize. It does not really learn very much from little data. It can overfit, so it doesn't really generalize to new domains that easily, unless you have good data for the new domain. If your data is too unstructured, then also it may not be a good problem for machine learning. So what do you mean by unstructured? Uh, one record doesn't look like the next record, one, something along those lines. So state of the art machine learning models, they exploit structure in the data. I'll come to this in a little bit. I'll show you what structure means. So if your model is too simple or explainable, okay, or explainability is desired, then you're better off using something from statistics or mathematics or physics. I'll give you some specific examples. Let's go to these. So let's first look at the sweet spot for machine learning. So if you have lots of structured data, it's just the opposite of what you had in the previous slide. If you have a lot of structured data and explainability is not critical, these models have become so complex that it's hard to understand why they make certain decisions. Just that they become very good at making those decisions or predictions. So if prediction accuracy is your primary goal, but explainability is not critical, then machine learning is the way to go. So and the underlying model is complex but stationary, then also machine learning is good. So what I mean by that is, you really can't like think of a algorithm that if you see this and see this and see this, then it is class A, or it is class, or if you don't see this, then it is class B. So if you can write it in those simple words, then it is not a good problem for machine learning. You are better off using something from statistics um, or uh, or mathematics or physics. So let's look at what I mean by structure, right? So the basic kind of structure that you will find in any data is basically a record type structure. So what that means is, let's say you have products and you want to predict the the volume of sales, and you have several different fields for that. What is the price? What is the margin? Perhaps the sale in the last year and so forth, and then you want to predict the sale in this year and so forth, right? So if you have a fixed number of fields for each row of data, then it is, you can call it a record. So there is a structure that every data point will have these 5 fields, every data point will have these 10 fields, these 100 fields. Then you know that there's a structure in that data, you can exploit that. Or you can have temporal data. So this is data that has a time order, right? So there is something that comes first and there is something that comes later. Examples of that is sentences in the language. You have a word that comes first, and another word that comes second, and then another word that comes third, and so forth, to make the complete sentence. Or audio signals, your pressure waves have a certain order, your certain phonemes come first, other phonemes come later, and so forth. So there's a structure, clear structure in that. Or you can have a spatial order. So if you look at images, for example, these images are made up of pixels. So for each pixel, so for example, when I blow up the eye of this cat, the center of the eye is dark, but you can see that uh, there are pixels to above a pixel, to below a pixel, left side and right side, and then based on that you can find that there are pixels that are dark and they form the boundary of the eye and so forth, right? And they are surrounded by light pixels and they form a line of dark pixels, something along those lines. So these machine learning structures, they figure those out to recognize that it's an eye of a cat and so forth. Uh, Another type of relationship between different parts of the data is a web of relationships. So this is akin to things like social networks. So each node that you see, each circle that you see could be a person, and each edge that you see is their connection to another person, such as they follow that person, or they're being followed by that person, or they are friends with that person, the other person on social media. Other examples could be molecules. So each of these circles would be the atom in the molecule, whereas the the interatomic relationships such as bonds and distances could be coded in these lines, which are called edges in the graph. So that structure has to be there, and then there are well defined machine learning frameworks that exploit these structures to give you better models and to give you better prediction. So the whole revolution in machine learning, and especially deep learning, is in the last 3 buckets: the temporal order, the spatial order, and the web of relationships. So now let's look at some ideal and not so ideal problems for machine learning, just examples, right? So based on what we have discussed so far, recognizing a thing, place, or person in photographs is an ideal problem because you are exploiting the structure of the pixels in the image, right? recreating speech from just lip movement, that is also a great problem for machine learning. So let's say you lost speech in some videos, you just see the person's lip moving. Can you recreate that speech? And there have been research papers that show that they can do it with very good accuracy now. Divide music into genres and then recommend based on the past likes of a person. So now here I would caution a little bit that yes, it will keep giving you the music of the same genres, but sometimes it becomes annoying when it becomes too predictive. And sometimes I get bored of the same genre and I want to explore. But I see that recommendation engines don't do that. They just keep repeating, giving me the same kind of recommendation that I'm used to. Whereas I'm bored of that genre after listening straight to that for like 5 days or something. Okay. Uh, some more exciting problems for machine learning are learning inverse models. So let's say given the performance of an electric motor, I want to design the motor, right? So how the stator and the rotor will be shaped, where will the grooves be, and so forth. I want to design that motor based on how much torque I want, how much efficiency I want, how much uh, peak current I want, and so forth, right? So that's not a trivial problem, right? But if I have lots of forward designs, I have design and performance paired together, right? And I have this not just from real motors, but I can simulate this in a physics software. Now I can take all these thousands of examples of motor designs and their performance characteristics to actually go back from performance characteristics to motor design. And this has been done in things like drug discovery. So we know all the molecules and their therapeutic characteristics that have been discovered so far. We code them up in, let's say, whatever is the relation number of hydrogen atoms. I'm just making it up, I'm not an expert in it. Number of hydrogen atoms, number of covalence bonds, and etc. And what do they block the EGFR pathway, whatever, what have you, right? And then now we can we learn this relationship in the reverse way, and then we can say that okay, I want these characteristics, can I design that molecule? And then now I have narrowed it down to a couple of molecules, or even like the other way around, I have thousands of molecules, I can see what properties they have, I can predict that now using a machine learning model, and narrow it down to 10 most promising molecules and just synthesize those. What is not ideal for machine learning, some examples, is predict the next solar eclipse. Why? Because it's a very simple model, right? It's just based on Newtonian physics. You can get very good answers to predicting solar eclipse by just using Newtonian physics. You don't need machine learning for that. Make a chatbot for an under-documented language. So here we have a dearth of data, right? So that cannot help you make those a language model or a chatbot for a language for which not a lot of data exists. So this could be a dying tribal language, for example, or an ancient language that we have just deciphered, and so or we want to decipher, right? Uh, Predict which company will become the next unicorn. Why? Because the economy keeps changing, the needs of the economy keeps changing, the rules of the economy keep changing, so the model does not remain fixed. So I would argue that it may not be it's not easy to predict which company will become the next unicorn, or it will become very difficult to encode it in a timeless manner so that the past data is predictive of future success for new companies that are coming in. We don't even know what technology will be in demand 5 years from now. Okay. Uh, then develop a comprehensive expert to replace doctors. So we can build machine learning systems to make very specific decisions in medicine, right? But a doctor takes a lot of context into account, and that context and a lot of that thinking of the doctor cannot really be captured, right? Or cannot ideally be captured. Sometimes, uh, so the machine would be limited by the specific test, not exactly that. Oh, I don't see that this person does has a limp, so it's also because they might have a kidney issue or something, right? So that kind of it there are too many unknowns, too many moving parts that I think it will probably be solved, but not in the near future. And then just for joke, you cannot predict the onset of next argument with your spouse. It's also a very ill-defined problem, and you cannot actually codify it into a structure. All right. Now let's look at one of the basic concepts in machine learning, which is model choice and rigorous validation. These are very important problems in designing and in testing machine learning problems. So if we look at model complexity on the x-axis and the error, right? So we want error to be small. We want this error to be actually small, right? So one way to reduce that error is to increase the model complexity, right? If you have a very complex model, it will learn everything that is there to be mapped from the input to the labels, and your error will keep decreasing. But it will decrease only for the training data, right? If you look at validation data on which the model is not trained, it is just tested on it, right? This is the held out data that the model was not shown for learning, right? You will see that the error will decrease, but after some time it will start to increase. What is happening here? Why does it increase? That is when the model starts to overfit on the training data. It starts to learn by rote instead of generalizing on the properties of the data, right? So if I have 1,000 photographs of dogs and 1,000 photographs of cats, and I have a model whose internal parameters exactly capture how to reproduce those 1,000 photographs each, then it will give you perfect results on training data. But that doesn't mean you show it 1,001th uh, picture of a dog or a cat, it will be able to correctly recognize which animal, which kind of animal it is. So there's a sweet spot in model complexity, and that's where the magic happens, right? So that sweet spot has to be found. uh, any model that is more complex than that is an overfit. Any model that is less complex than that is an underfitting model. So a lot of machine learning is about finding that sweet spot and actually rigorously doing that validation. I'll come to that in a little bit more. I'll specifically talk about what does rigorous validation mean. Okay, so what is complexity anyway? What is model complexity anyway? Let's look at simple models, right? I'm sorry, this is the only slide that has mathematics. Okay, so let's look at a simple model. So let's say your output of the model is y, that you are trying to, that is a prediction made by the model, and the input to the model is x1. So the simplest model that you can have is an equation of a straight line, which is w1 x1 plus w0. You might have seen it as mx plus c, right? So that's the simplest model that you can have. One input, two unknowns. One input is x1, the unknowns are w1 and w0. Now let's say that one input is not enough to model uh, the output correctly. So you add a second input. So for example, let's say you are trying to predict customer behavior. You are using only the last purchase that they have, the total ticket of the last purchase. Now you also want to add how frequently they come to your store, so that becomes an x2, right? So you can add more inputs and make the model more complex. You can change the type of function, make it more nonlinear instead of this linear equation, and it will become even more complex. You can you can put several nonlinear terms in the function, and then you can add, because you have more terms, you have more weights that are to be determined during the learning process. So all these weights have to be determined during the learning process, and the model becomes more complex. And then you can add functions inside functions, so that becomes layers of functions, which is what a neural network is. So that way you can keep increasing the complexity of the model, right? So your modern machine learning models have thousands of inputs, tens of thousands of input, hundreds of thousands of input, and millions in for example, GPT has crossed that, even the millions thing that we had in mind. It is a very large model, right? It's in the billions. So uh, these have at least millions of parameters, if not tens of millions, hundreds of millions, and billions of parameters. So increasing complexity means you are using more data more dimensions of the data as input, and you are using more number of data points, so more images, more text sentences, etc. Because to train complex models you need a lot of data, and you have more parameters, these weights that need to be determined, w1, w2, w4, uh, which run into millions of them, to model complex relationships. So this is where this is a sense of progress that deep learning has made, right? So these are the years that you see on the x-axis, and y-axis is accuracy on a benchmark dataset called ImageNet. This dataset has over 14 million images. 20,000 classes such as cat, dog, but not just cat, dog, but different types of cats, different types of dogs, uh, airplanes, cars, uh, everyday use objects, 20,000 objects, right? And they have to be correctly classified. And your the top 5 out of these 20,000 classes that have to be predicted should contain the right class. That is the metric, let's say, we are looking at, right? So these you can see that we started with top 5 error of just 16% in 2012. This is when the first time the neural networks were ported to a GPU, right? So after that, it just took off. After that, the error or accuracy kept increasing, error kept decreasing. Uh, Soon it was 7% error, 6% error. Human is around 5% error. So now it has become superhuman in terms of error. It has now 3% error and 2% error. Right? So there's a general trend of course, decreasing error, increasing accuracy as we go up. There's increasing accuracy over the years. Uh, but you will also see that not everything has come at us at the cost of size of the model. Size of the model means the number of unknowns in the model. It started with 62 million, 138 million. Then people started experimenting with new structures within the neural network, the new way of connecting the neurons that did not require as many parameters. So size of the bubble is the number of parameters related to the number of parameters. So then there was a jump in accuracy with fewer parameters, and then again the parameters started bloating up, and then someone came up with an even more nifty structure, and the number of parameters went down again. So what does this beating the human accuracy means? So many times the images are such that, so for example, you could have a husky and and a grey wolf. They look very similar, and some humans will get confused, so they will make some error. However, we know that from some expert humans who were expert in that domain, they labeled the images correctly when they were preparing the data set, that this is a husky and this is a grey wolf. So from that we know that the true labels are husky, grey wolf, and the machine is able to recognize those subtle differences that expert humans in that domain. So out of 20,000 categories, every human is not an expert in every all of these 20,000 categories, right? So some are expert in some 500 categories, some are expert in another 600 categories, and so forth. So all that knowledge combined, neural network is starting to do better than an average human. So what are some other considerations? Is it that we always want the most accurate model? No, not of course not. Right? You have to think about where the model will be used, and how it will be used, and so forth. Right. So we have to think about how much memory it occupies, how much memory it occupies in terms of just the model itself, or in terms of actually running the model. Is it transferable from one set of images to another set of images? Can we repurpose it very quickly? How much computations or power it requires? So can it run on edge device, for example, right? Or do you always have to ping a server? How much server price do you have to pay for each ping, etc. Right? And then speed and parallelizability. Some models are more amenable. Some types of machine learning frameworks are more amenable to speed. Some are more amenable to parallelization. Right? Uh, and all this talk about different ML models is a small part of the entire life cycle of ML. So let's look at the life cycle, right? So it starts with need identification. What is it that I want to solve and potentially use ML for, right? And after that, I will start to gather data, right? And I have to answer questions such as, is it the relevant data that will help me solve the problem? Is the cost of collecting this data too high? Okay, is there are there ethics involved, ethical considerations involved in gathering this data? Can I store this much data, etc., etc.? And then comes model choice. Once I know what data I have to collect and so forth, and then what model exploits the dependencies in this data, okay, to the best extent, right? And then I will do training and validation, and then I will deploy the model. Once I deploy the model, so there are different kinds of deployment scenarios. Just like I mentioned, that it can be on an edge device, it can be on a server, it can be on a desktop. So we have to keep that in mind as well. And then finally, we have to monitor the performance of the model on an ongoing basis. So some of these are completely overlooked when we think of ML, right? So most ML courses will only talk about model choice based on the data that is already gathered, right, and training and validation, whereas there are all these other things that we have to also worry about. So we may have the best performing model, but at deployment we find that it actually drains the phone battery too much, or it is costing too much cost from the server company on which we deployed the model and so forth. So we have to go back and question some of the choices. And if you go back to any of these stages, you cannot skip steps, right? You have to go through all the steps. So from deployment, if I go back to need identification, then again I have to assess data gathering, and then and then model choice, and then training and validation, and then come back to deployment. An often overlooked part of this entire life cycle is monitoring, right? So once it is deployed, how is it being used? Is it are there is it being used in scenarios for which we were not prepared, and so forth? So let's explore some of these questions a little bit more. So what are some of these overlooked questions? So are we solving the right business problem or the societal need problem, right? So that is the biggest thing that we should talk about. That oftentimes it's not in the purview of engineering, but someone who's taking these larger decisions should be thinking about these. Then data and provenance. So do we have diverse data? Do we have enough data? Do we have relevant data and representative data? Was it ethically gathered, stored, transmitted? And do we have we meticulously recorded what kind of data we gathered, and so forth? So a lot of uh, bad PR and ethical questions can be raised. For example, the if we are working on face recognition software that is trained only for one race, and now it makes some bogus predictions on people from another race, and you have seen these cases in the news lately, right? So data and provenance are some of the biggest concerns that one should have while thinking about holistically about machine learning. Okay. Then a model we have already talked about. It should exploit the structure, and the data should be sufficiently complex, not too complex, and it should meet your um, deployment constraints of power, of cost, of compute size, etc. Now, and then this is another important aspect of machine learning that is often overlooked when you work with benchmark data, that your validation should be on realistic data and not too optimistic a scenario. So let me give you an example. So let's say you are working on detecting cancer from a particular pathology scanner, right? And all your images were scanned using that scanner, and they came all from one hospital. And you did the due diligence of separating the patient for training and validation. You trained on the training patients, and you tested on the validation patient, and you got very good results. Does that is not a realistic scenario for validation. It should have been tested for patients from another hospital whose pathology slides were scanned from on a scanner of another brand, unless you can enforce that it will only be used in one kind of scanner brand. Why another hospital? Because the kind of patients that go to one hospital could be very different from the kind of patients that go to another hospital. One hospital could be catering more to patients from a certain ethnic background, or those from a socio-economic background whose so these could be patients from a different socio-economic background, um, and it could be patients. Consequently, it could be patients who only report to a hospital when the cancer is already higher stage. So for higher stage cancers, the tissue looks slightly different, right? So all these things have to be kept in mind when we are thinking about validation, uh, and it should cover diversity of use cases, and the performance metrics should be meaningful. Let me give you an example of that. Someone comes and says that my I can detect cancer with 95% accuracy. Well, what does that mean? What does that mean about missed detections or false alarms and misdetection? So you have to look at both of these things, not just one of these things, right? The false positive cases as well as false negative cases. And then user guidance. Did we declare the intended use case to the users? You're selling knife for cutting vegetables and someone uses it for surgery, right? So I mean that's a trivial example, but that it's not so obvious that this is a knife for cutting vegetables and not for surgery when it comes to AI. So that declaration of intended use case, whether it's an entertainment AI or is it a serious AI, that should be declared, right? And the description of the data used for training and validation should also be there, that it was trained on this and it was tested on this, and then this is the performance metric, and performance from both sides, the positive side and the negative side. And another often overlooked aspect is monitoring in-field performance, right? So once it is the AI model is being used, are there differences in data? Was it trained on a different kind of data, but now it is being used on a different kind of data? Like for example, ethnicity of faces, the stages of cancer. In driving, it could be it was trained on in New York, the autonomous driving vehicle, but now it is being used in New Delhi and so forth. And what about concept drift? What that means is the scenario has changed. It was trained in New York, now it is being used in New York, but there was a new construction in New York or new rule in New York where pedestrians can jaywalk wherever, and now the model was not trained to for this new scenario, right? Uh, this concept drift can be, let me give you a better example. You want to recognize people's ages and you trained it based on the full body shot, and people of different ages wear different kinds of clothes, but the fashion changes, right? um, and then was your model being used for unethical or unauthorized purposes? So for example, we used it for entertainment, we trained it for entertainment, now it is being used to actually uh, to for some more serious purpose for which it was not intended, and it was unauthorized even. So now let's try to apply these questions to some of these scenarios. So after each scenario, take a little bit of a pause this video and think of what questions you will ask. You can even discuss with someone who's next to you. So for example, let's say someone comes and tells you that we need to store every keystroke and mouse movement of use of company computers so that we can run ML on it later. So what kind of question will you ask for this? So immediately what comes to mind, what will I use the ML for? What is it that I want to predict? And is it even ethical to store such data? What is the cost of storing such data? This is a huge amount of data. We might have, this is like every 1/10 of a second are we storing this, whatever that is, right? So it's a very ill-defined statement or need that someone has put forward. Let's take another example. Our product can give biometric access based on face recognition. No need for cumbersome fingered ID or iris scan. What question will you ask? Right. So immediately what comes to mind is what is your accuracy? I want the accuracy to be 99.5%, right? Because I don't want people to be frustrated with an 80% accuracy that every fifth time it doesn't work, right? And then what does that accuracy mean? What did you train on? Did you train on people uh, from a certain ethnic background? Did you train on people with certain like real background? What is behind them? Will it work on in new scenarios where the lighting is different, where the background is different? Can you demonstrate it? Right. So what is the false positive rate? What is the false negative rate? So all these are pertinent questions to ask. Like just we have an ML system is not a good enough statement. We can detect pneumonia in chest X-ray with 99% accuracy. See, this 99% accuracy does not mean anything, right? So if this 99% accuracy is based on a population study, and 99% of the people in the population already don't have pneumonia, and chest X-ray just says no pneumonia, no pneumonia every time, you already have 99% accuracy, right? So it doesn't mean anything. You have to ask them what is the false positive rate and what is the false negative rate, and can we do a trade-off between these two for something that is workable? No ML is going to be 100% accurate, obviously, and both sides of the mistakes have to be taken into account. The other questions you can ask is, well, when you talk about chest X-ray, was it based on scanned film X-rays or was it based on digital X-rays? Was it based on digital X-rays of vendor A or of vendor B, or both? And will it work on vendor C? Those are again good questions to ask, right? So you have to think beyond just like an accuracy metric. We can recognize people's emotions with 91% accuracy from their faces as they watch videos on our website. So this is an ethical landmine, right? Did you get consent to tape them? Uh, what does it mean 91%? Is it that most of the time they are bored, so you can easily predict 91% accuracy? Uh, what will it be used for? Did you get the consent on that? Uh, is it was it all based on in your company's conference room where the types of people and the background is quite not so diverse, or was it tested on a much wider audience? What was it tested in like different continents and so forth? Our video call plugin can tell when people are lying. Now, again, this is an ethical landmine. What will people use it for? Is it just for entertainment? What kind of people was it trained on? What kind of people was it tested on? Were the lying scenarios were the lying scenarios acted, or were they like actual natural lying? Uh, did people know that there is someone who's recording them who people can change their expression when they are under they are told that they are being watched by AI and so forth. Were they expert liars and so forth? So there are lot of things that you can ask to probe further about any such statement. Our autonomous vehicle is 20 times safer than an average driver. Again, what was it trained on? Was it trained in New York, and now it is being now you're trying to bring that into New Delhi? Very different, driving scenario. Trust me. What does it mean 20 times safer? Is it like based on per mile driven uh, compared to a human average number of human accidents? What was it tested in snow? Was it tested in heavy rain? Uh, if it was just tested in fair weather, was it tested on icy roads? So all these questions are pertinent questions to ask. Uh, when should the control be given to human? If it was not trained on, let's say, icy roads and so forth. On the other hand, you can also ask the question that if it is truly 20 times safer than an average human, then should it be legal for a human to drive and take that risk and subject others to that risk? So, that is also a good question to ask. Okay, so where is ML research going? Okay, a lot of it is going towards reducing the data requirement because these large models are very data hungry and computation hungry. So when you reduce the data requirement, you also reduce the computation requirement. So the way it works is that you pre-train the model on other data. So for example, training with unlabeled data. Getting labels is very difficult, right? So you have to take each image, each text, or each audio sample, and you have to put a label to it that this audio sample is the word this audio sample is the word him, etc., etc., right? So all that is a lot of effort. So training with unlabeled data, how to come up with training algorithms for that. Training with fewer labeled data, so that's called few shot learning. The unlabeled data is self-supervised learning or unsupervised learning, mostly self-supervised learning. Then training with high level data labeling. So I'll give you an example of, I'll tell you what the whole sentence is, but I won't tell you where the words are chopped. So that is something called weakly supervised learning. Okay. Take learning from one task and take it to a new task. That is called transfer learning. So if I take learning from classification of flowers, does that translate to classification of different types of whales, for example? Right, so some of the underlying structures such as looking at the edges and colors might be the same, so that a lot of these neural networks are amenable to transfer learning. Design models that can explain their decisions. This is going to be the frontier, because right now these models, they are very good at predicting, they are very good at predicting the labels, but then they cannot explain their decisions. To some extent now they can tell you where they are focusing on, which is called attention, but that's pretty much it. They can't tell you what is it that they are focusing on. Where they are focusing, they can tell. Make models more cautious by recognizing new scenarios. So this is called calibrated models, or models that can recognize their own uncertainty. So you train a model to recognize certain mutation in grade 1 cancer and you throw grade 2 cancer at it, or a different histology, a different type of cancer at it, it should say, oh, this is not something that I've seen before, so I don't feel comfortable making a decision on it, or I'm unsure of my decision on this. That is, I mean, it won't say in those words, but basically that's what you train the model to output, that whether it is certain or uncertain about its prediction. It should not be overconfident. Currently, the widely used models, they are accurate, but they are overconfident even when they make errors. So now, with all this background, you should be able to answer this, right? Is it a myth or a reality? Let's talk about these. AI is constantly learning and improving on its own, right? So that is a myth. There are a class of learning algorithms called online learning, but most of the AI is not constantly learning. You take data, you take labels, you train the AI, and then the engineer comes back in another month or another day or another year, collects more data, and sees for the past data what kind of errors were being made, and based on that changes the model and retrains it, and plugs in the V2 version 2 of the model. So it's a very manual process. A lot of it is being automated slowly, but the AI is not constantly learning and improving on its own. AI can be self-aware. This is another big myth. Not currently. It's probably, we are several, few decades away from it. Currently, most of AI is just pattern recognition. So you give it an input, it tells you the output. It is not self-aware. Doesn't have needs. Doesn't have needs for survival, for love, for reproduction, for eternity. Nothing. One needs large investments to get started in AI, and this is another myth. A lot of it is the hardware, the software, and even the frameworks are being commoditized. So for example, on several cloud services, you can train AI models for very cheap if you are doing it in a short term. For the long term, with a few $1,000s, you can get your own rig to train AI models. Not the big, large models like GPT-3, but some of the other models like ResNet and so forth, you can train on your own. You can even train them on free services provided by some of the big companies. AI is only for whiz kids. No, again, a lot of the software and even the pre-built code for AI is being commoditized. It's being released for free under very generous licenses by their inventors, and that's one of the very exciting reasons for me to be in this field, because that reduces the barrier to entry for innovation. You can start with someone's building block and make small changes and see how it performs, how the improvements work out. So it's not for whiz kids anymore. The true innovations are coming from the whiz kids, but for using AI, uh, I even someone who doesn't have a very strong math or programming background, I have heard of radiologists who have learned to use AI, uh, provided you have the open mind and to work into this. AI will only replace mundane jobs. Again, this is partly myth, partly reality. The reason it's a myth is because now there are AIs that even generate new art, for example. Now, will you call it an art? Will you appreciate it? Just a pen stroke or brush stroke of Picasso, people start to interpret some things out of it, but will you do that for something that is generated by a machine? Maybe not, but AI is already like getting into creative fields as well, so it's not just mundane jobs. I talked about motor design. That's a very highly specialized skills for which you have to go to 4 years of college and then probably a master's or a PhD, and then or perhaps several years of training in the industry to be able to design motors, right? And that is now you can do that using AI. So it's not like it is replacing humans, which is the next point, right? AI will completely replace humans in most jobs. It will become an essential toolbox for most humans to become highly productive. Where it would take me 5 months to design a motor or a molecule, going through all those experiments, testing it out, I can do that in computers over a few days and then come up with the best candidates on which I want to physically test the reality. Okay. AI cannot be easily fooled. No, that's another myth. There's a whole line of research on how AI can be fooled and the countermeasures on how to make it more robust. So that is called adversarial learning. AI can easily be fooled even in ways where humans will not be fooled. You add some subtle noise, intelligently put subtle noise where For a human, the image still looks like a dog, but the AI would be confused and call it a car. Uh, so that works with the algorithm that is used to train AI. That same algorithm can be used against it. AI can make sense of messy data. No, clean data is what it is. You need structured, clean data. Uh, you can have like some kind of noise and so forth. There are robust AI training mechanisms, but for the most part, it doesn't. You can't just throw data at it and expect it to come up with something. It has to. The problem has to be very, very well defined. Only in well defined problems, like I talked about ImageNet, right? It's a very well defined problem. Uh, in ImageNet, it is beating human accuracy. But even in those images, if you ask AI to say that, do you see a joke in it, in this picture, right? Does it remind you of a movie title? That same AI model will not be able to do it. You'll need a different AI model for it. So it's not a generalist, right? So we as journalists can make sense of messy data. AI cannot. It is very, very highly specialized, and you have to think of problems in a very crystal clear manner. AI can predict anything very accurately. No, that's again not true. Sometimes the data that you have collected to predict something is not enough. It doesn't capture the enough relationships between what you want to predict and what you have. Right? So it cannot predict anything highly accurately. Don't expect 100% accuracy. Don't expect 99.9% accuracy in every case. Some problems are genuinely tough. So, for example, looking at a patient's pathology scan, which is what I work on, and saying that whether this patient will die in 3 years or 5 years or 7 years, it's not an easy problem even for AI, right? So there are, because that's a very small window into the patient, there are many other things happening inside the body of the patient that are not captured by the data that you have captured. So these are for complex systems such as human bodies, economy, etc., uh, and several other things. AI will not be able to predict very accurately. Okay, so this is my final slide. Let's talk about the takeaways. What did we talk about, right? So AI is not a silver bullet, right? Don't expect it to answer all your problems. Right? Not necessary. AI is not necessary for simple models. It does not work well with ambiguous, general, and unstructured data and scenarios. Do not expect solid explanation from ML predictions anytime soon. For ML predictions anytime soon. Uh, AI research is moving towards that direction. For now, it is good at predicting, but it can't explain its predictions. Our best bets are that we have provenance, which means we know we keep track of what data AI was trained on, what data it was tested on. Rigorous validation, the way I talked about. So think about a realistic scenario in which you want to apply AI, and monitoring its use and performance on an ongoing basis. So it is still very useful. Okay, it can go beyond human level capabilities on well defined tasks, especially with structured data. And the data is the currency of ML. So a lot of ML is now commoditized. So you need relevant data, you need clean data, and you need realistic data for your scenario, and that is where you will have an edge. Okay? And whenever you have an AI model or someone making a claim about an AI model or a system, you have to critically test it, critically question it. Only then you can accept it. Even at the design stage, you have to think critically about how it will be used, in what scenario it will be used, what will be the constraints of that scenario, and so forth, and what will be the cost of putting it in that scenario. So all that has to be thought about when you are looking at ML models. Thank you.